So I think that we have 10 minutes for discussion. Any questions for our speakers? I see two questions, which is kind of answered by Professor Bray, but maybe we can, revisit them. So, Amanos, can you give access to kind of Artie to ask his question?
Yeah, I will just do that.
Yeah, I think that he can talk.
Hi there. Yeah, this is Artie. I don't know if you can hear me.
Yes, we can.
Yeah, I had asked Professor Bray some questions. I mean, all the talks have been really great and really outlined the importance of characterizing geotechnical properties and showed evidence of strong or very short wavelength variations in geotechnical properties. For those of us who run simulations, we'd like to be able to incorporate, there's obviously the need to incorporate finer scale geotechnical structure into the models. And I was wondering if Professor Bray could comment about sort of how would we go about collecting that type of data on a very fine, in a sort of campaign style, to then incorporate, have these available so they could be incorporated either into the Earth models used in simulations or as part of the interpretation and post-processing of simulation data. Thanks.
And I thank you for the question. And I did answer it in writing. I think everyone has access to that, and so they can look through that. It always depends. And I was thinking about it a bit more as you're asking the question. And I think a key thing that we do on important projects is we have limited budgets, and we're never going to have enough money to cover the entire area as well as we want to. And so getting representative areas and saying, instead of characterizing every place, if I find this as kind of a reasonable model, do a very detailed assessment using surface wave, shear wave velocity measurements, using the CPT, which is excellent for profiling, and making that and the statistics and the variations laterally of that zone a model for then the other areas that you think are somewhat like that, adding some epistemic uncertainty because it won't be exactly like that. I think that's achievable. I think that we can put out instrumentation that captures things on a close network, and then we can add in detail in representative areas that can then inform the models that you're looking at. And just jumping forward, the follow-up question that Artie mentioned was, can we do that? And you would think yes, because it's very important, but our history has shown, the Seismic Mapping Act was enacted after the Loma Prieta earthquake and the Northridge earthquake, and the mapping and all the detailed site investigations that were done in Christchurch was after this devastating sequence of earthquakes. So we should not give up, and we should talk to stakeholders and get them involved and get them motivated to do these types of things. But we should also be prepared that this is something that might have a window of opportunity after an earthquake, and using aftershock recordings and then going and saying this campaign is necessary for the next earthquake. That's something that we have to be prepared to do as a profession.
Well, maybe for the panel then, it seems like if, using geologic maps as a way of guiding, the interpolation that you described, to go out and make measurements and then associate them with different geologic structures, and then allowing some, geospatial interpolation that's informed by the geologic structure would be, maybe take us a little bit further than what we have now at reduced budget. If you think about, we would like for simulations to have geotechnical information probably on the order of 100 meters or so, and that's 100 measurements per kilometer, and we simulate 10,000 kilometers. So that of course we're only probably need to look at the soils and the urban areas. I think you'd agree should be prioritized, and then the critical infrastructure. But yeah, I understand it gets expensive.
Okay, great. Dave, please go ahead.
Yeah, this is a challenge. I thought Jonathan did a great job of framing this and a good reminder to us all who have a tendency to forget about the geotechnical layer when we're doing these large scale simulations, you know, a good reality check to sort of bring us back down and put it at the forefront of our thought. Elnaz, I was interested in the simulations you were doing, which is sort of an initial foray into doing nonlinear simulations at scale. But the factor of 14x scares the heck out of me. And it really makes me wonder whether it's truly scalable to a high frequency simulation in a large domain.
Yeah, honestly, so far we kind of wanted to make sure that we can use the model which is doing right, and then see what are the effects, basically. We haven't done any validation, nothing, no improvement in terms of being scalable. And I think that but that is the most important part. If we really want to model nonlinearity at the regional scale, we need to develop scalable scalable software packages, or maybe we should come up with some other strategies if the nonlinearity is really localized. Maybe
yeah, so that's
come up with other
question that I was about to ask. Is if you think about the Bay Area, it's very shallow basins or very shallow sedimentary deposits compared to, for example, with Los Angeles, and relatively localized. And you talked about a 3D, 1D hybrid. And I just wonder if there's not a 3D, 3D hybrid where you have a nonlinear representation of these localized near surface layers that maybe you couple through the domain reduction method to your larger root model. And I think you might have thought a little bit about that. So I just wonder if you would comment a little bit about something, any strategy you might thought of for handling this very, localized characteristics in this global model.
Yeah, that's true. We discussed that a lot with you and also with Dorian, that maybe we can come up with the regions that we think that it can go nonlinear, and with the assumption that probability is localized, we can do that simulation. But at the same time, to kind of verify our kind of hypothesis, we can do the fully nonlinear simulation and see what happens. If we really see that the results are not that different, then of course, having basically somehow solving a I don't know, should we call it physics or scale, a problem using even the same platform, but at different scales, or maybe a coupling between different solving platforms. One can go nonlinear and the other one can be maybe SW4 or Hercules at a very large region, let's say.
It's so important, clearly. And it just, to me, there needs to be some very clever computational thought about how to localize this so it's actually computable, right, at scale.
Yeah, that's true, yeah.
Thank you. And
Sure.
John, really appreciate your presentation. That was great.
And I think that we have time for another question. Floriana, do you want to ask your question?
Yes, I have a quick question for you, Elnaz. So it was a very nice presentation, and I was particularly interested just by those contour plots that you showed, where you compare the linear and nonlinear response for your soil island. And so you showed comparison in terms of PGA and PGB. So I was wondering, first, how does you model the damping? So if you're relying only on the hysteresis damping coming from your nonlinear material, and then if you just have analyzed how just damping and your nonlinearities get reflected in the spectral acceleration, particularly at very high frequencies, well, depending on the resolution of your model, and then at the very long periods. So if you have just given some thoughts to that.
Sure. For the damping, we have two types of damping. One is for both linear and nonlinear. Of course, some of the elements can stay linear. And for those simulations, we set all the elements with the shear wave velocity more than 1 kilometer per second to be linear. So for those, we are using the existing attenuation models that are in velocity models, some typical value for that. And for the case that elements goes nonlinear, on top of that, we have, of course, the energy dissipation in terms of material damping. So that is the way we are kind of modeling or incorporating damping in our model.
Okay.
What was the second part of your question?
If you have analyzed also the impact of including the nonlinearities in some analysis in the frequency domain in terms of like spectral shape. And so if you see any amplification at long periods, although we know just there should be just not really pronounced, and some de-amplification at just shorter periods or higher frequencies.
We had significant de-amplification for higher frequencies, but not necessarily de-amplification for low frequencies. That was somehow our observation so far for the peak ground acceleration. But of course, for displacement, the story is different, and we can have the amplification or increase basically.
Okay. Okay, thank you.
Sure. Okay, so maybe we should move on to our next session. And before that, we have
one more question from Robert Graves. If you
Sure.
want to see if the
yeah, sure. I think that we can take that one.
Robert, you can speak.
Can you hear me?
Yes, we can.
Yeah.
Okay, great, thanks. Excellent talks, everybody. A lot of impressive work. I kind of have a comment, but maybe the panelists can then comment on my comment. So the attention to the near surface or the geotechnical layer is obviously very important. My comment is that I think we also need to be aware of what's below that. So, we talk about seismic bedrock or maybe, 1,000 meters per second and so forth. Many times, like, in these community velocity models, that layer or those layers, kind of just below the GTL are actually very poorly constrained. And so it's, what that, say, the site-specific parameters that might come from a detailed geotechnical analysis might be sitting on something that is very poorly constrained, and that might impact what happens. So my comment is that just we need to kind of think about how all of the components of the model couple together. It obviously makes the problem much more complicated, but maybe there's some leveraging that can be done too in terms of how the analyses or how the site investigations are done. Using different types of geophysical methods and things like that. So that's just my comment. If the panelists would like to further comment, that would be great.
Great comment. Thank you. So, John or Hiroshi, do you want to talk about that? Any comments?
Well, thank you for raising that kind of aspect of the studies. That is very important to me to see how precise that our community model is represented in terms of the depths down to the seismic bedrock, because even though the impedance contrast between the seismic bedrock and the surface is high, the waves is going up and down and then reflected back to the surface. So that without considering the seismic bedrock, the real wave propagation phenomena cannot be made. Only the surface, shallow surface structure amplified a lot. That is true, but it is only a part of the whole story if we are seismic waves.
And I know we're short on time, but I'll just state that it's obviously an important aspect and it has significant uncertainty. I think it's more important for the longer period, and it's more important probably for these deep, stiff soil sites. The positive aspect, if you can call it positive, is that when you get to these soft clays, they really do take whatever you're giving them, and they really do have a signature that affects buildings in that period range. So it depends.
Well, that's the point. The fact is that not only the long period, but also short period is strongly influenced by the depths down to the seismic bedrock, because, say, 5 hertz ground motion is come up to the surface and go down to the depths and then coming back again to the surface, so that we see the resonance of the whole basin structure from 0.1 hertz to 20 hertz. That's the point.
Okay, great. Any other questions? All right, so let's stop it here. I think that we have time for kind of 5 minutes break, and we will be back at 4:55